Good morning, viewers. Welcome to the day 2 of COSCUP. It couldn't be better to start a day with an odyssey from resistance to embrace. It's our great pleasure to have the CEO and CTO from QuickLogic joining us. QuickLogic is an FPGA company. For people who don't know what an FPGA is, it is a specially crafted chip that could be programmed to contain custom logic designed by you. In the past, tool chains for these very useful devices were sadly closed-sourced. And acquiring license for such tool chains is often painful and obnoxious. But now, things have changed. Without further ado, let's welcome the heroes who set their FPGAs free, Tim Sachs and Brian Faith.
Thank you, Renlin. And good morning, everybody, to all of you in Taiwan. I'm Brian Faith, the CEO of QuickLogic, and I'm thrilled to be here at COSCUP today, virtually to be sharing our story, followed by an awesome demo by Tim Sachs, our CTO there. So, without further ado, QuickLogic is an FPGA company. We're actually a programmable solutions company. So we have FPGAs, and we have microcontrollers that have FPGAs on them, and we have embedded FPGA cores. We primarily focus on the low power space. So you can see different markets there, like IoT devices and consumer electronics devices. And there's an amazing amount of devices today that use our technology. And I hope that you are inspired by some of the things that you see today from Tim. So what is our journey? We started as a company about 30 years ago, and we've done lots of different programmable devices. And one of the favorite trivia questions I have is for people to guess how many programmable logic companies have come and gone in that 30 years. And of course, the answer is shown there. So it's an easy question, but it's more than 60. It's a crazy number of companies that have come and gone from FPGAs. And it's amazing because there's so many architectures and great products, and you got to wonder, why did so many fail? And really, it all points back to software. Almost every single one of those 60 companies had devices available on their shelf, silicon devices that were made and manufactured, but their software just wasn't good enough to take advantage of the silicon, except for those who did, like QuickLogic. We had a nice situation where our software worked and we're able to sell our devices to customers. And so that creates what's known as this walled garden. So FPGA companies love to have people use their proprietary software because once you're inside the garden, it's hard to get out. And that's also called vendor lock. And customers and users usually don't like that. They like freedom to choose. We like choices. But the traditional FPGA approach is not to give choices. It's to lock you in. So this was a journey that began about 2 years ago for us. We were talking with many people in industry, also a gentleman in Google who's also presenting here, Tim Ansel. And he convinced us that we should actually go and do open source. And he invited Tim and I to a show, an open source show called the OR Conference in Europe. And we went there, Tim and I, and we were blown away by the quality of results of the open source tools. It was amazing. And that visit to that show, much like the one that you were attending here, really convinced us that we needed to take the leap and do it also as the first FPGA company to join the open source FPGA tools movement. So we launched that about a year ago today, or a year and a month ago. So with that, going to the next slide, we launched with our FPGA family. It's a microcontroller plus an FPGA, as you can see there at the bottom. And you can do some really amazing things with microcontrollers. You can do some amazing things with FPGAs, as Renlin was saying. And what we did with this whole open source approach was launch with open source software, meaning FreeRTOS and Zephyr, open source hardware. And we've got so many different boards now. I've got all these ones here on my desk, but you can get them from different places around the world, different distributors, and start really innovating neat little products with these. And the neat thing I think about open source is that once we put out products like the Zephyr and the FreeRTOS operating system on the M4, and we got SymbiFlow support for the FPGA, the community took that and ran with it. And so now there's MicroPython support and NMyGen support. These are things that would have taken us a long, long time to do, but the community did that, and that was really awesome to see. And that's really the power of the open source community. What we did with that is we actually launched this climate change challenge between QuickLogic and our subsidiary company that has AI software. And we challenged the community to come up with the best line-powered and battery-powered proofs of concept to impact climate change in a positive way. And we got all these neat submissions. And really, this was only possible because we had all of the package in open source and the community ran with it. So it's really inspiring to see what people can do with open source hardware, open source software, FPGAs, and microcontrollers. So very cool to see. So with that, what's next? After you have FPGA and real-time operating system support, what can you do with that? And there was a university in India, in Hyderabad, that took the SymbiFlow tools and they actually got it to run on a smartphone. So now think about that. You don't have to have a PC or a laptop to actually do FPGA design. You can do it with your smartphone. And you can imagine that if you can start doing FPGA design in a smartphone, how many people in the world can use FPGAs? I think that's mind-blowing, and I think it's very inspirational to think about that. And that's sort of leading us to this next initiative, which is the Open Source FPGA Foundation. If people are doing this sort of on their own, what if we actually had a foundation that was really with the whole vision of proliferating that technology to everybody? And the only way that's possible is to lower the barrier. And if we can lower the barrier of adoption by making it easier to use, making people understand FPGAs, then I think you're going to see the next million FPGA users in the world in the coming couple of years. So I just give a plug for the Open Source FPGA Foundation. It's free to join. You can get in, you can join the technical works, technical groups, and really start to further everything to do with FPGAs so we can really achieve that vision of everybody knowing what an FPGA is and using an FPGA. So that's a very short journey because I think you're probably more interested in what Tim has to say and show you versus me. So with that, I'll just say FPGAs are definitely here for good, for prime time. Open source tooling is here for prime time, and we're really happy to be part of that movement. So without further ado, I will turn it over to Tim, and I will stop sharing and let you share, Tim.
Great. As soon as I can figure out how to share. Ooh, that's not going to work. Hang on 1 second. Share screen. Two monitors.
We haven't seen your screen share, but okay, I see. Okay, put it on the front stage. Okay.
Cool. Okay, so let me just put this in slide mode. Great. Sorry, now it's kind of flip screens on me. Let me go back and undo that. I'll just make it really big here. Okay, so might be good to start at the beginning. So the beginning for us, or for most people's journey with us, is with GitHub. And there's a QuickLogic Corp GitHub website, as you might expect, or location. And pinned at the top are a number of things. So the one I'm going to start with is the QuickFeather development board. That's one of the many boards that we support, but it's a good place to start, one I'm familiar with. And if you go in there and open it up, it says, oh, here's a development board that you can get. It's a small board. And as it says, it's open source, so you can get the layout for the board, everything like that. We worked on this with Ant Micro, who's a big open source supporter. And it's compatible with the Adafruit Feather ecosystem. So you can get small wings that plug onto it. So if you want to add various things like, ADCs and so on, it's easy to do. So a lot of people in that Hackster contest use this. If we zoom in on that board, there's this EOS S3 device, And that S3 device has a bunch of stuff in it. It's got all the normal stuff you'd expect for a small MCU these days. So it's got a Cortex M4, runs at 80 megahertz. It's got SRAM, it's got DMAs, it's got SPI, it's got I to S, it's got I to C, and all this kind of stuff. So it's a conventional MCU system. There's a lot of those. But what we're going to do is zoom in on this little area here called the eFPGA, and we're going to address the question of, well, how could I use that FPGA? Now, you can do a lot of stuff with FPGA. It's programmable hardware. So what I want to do is show you how I used it for a particular application to give you a feel for how easy it is to do this. So if you want to program the FPGA, of course, you need a tool chain, and there's a fast tool chain for that. So if you go to our website, you can see that. It's the QuickLogic FPGA tool chain, it's called. It's built on top of SymbiFlow. In fact, it's mostly SymbiFlow. It's just a little repackaging to make it work with our devices in our environment. So that's great. That makes it easy for people to use. And there are two fast chains for the rest of the chip because the FPGA on itself, while it's nice, it's plugged into a chip. So you're going to need a tool chain to run the rest of the chip in order to talk to whatever happens on the eFPGA. So we have tool chain of Quark SDK, and we have Zephyr. And the example I'm going to use the Quark SDK for that. So if you look at the Quark SDK, repo, you see it here, you'll see that there's a bunch of stuff in there that you normally expect to see. You see a board support package, FreeRTOS, HAL, libraries, tasks, blah, 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 blah. And there's a lot of goodies in here. There's examples for the QuickFeather chip. There's examples for QOMU, which is a very small thing that plugs into a USB. There's examples for QuickThing Plus, which was just recently released by SparkFun. And there are also VR app examples. Unfortunately, all of those rely on a proprietary VR engine. But if you're interested in seeing how you manipulate audio and stuff, you'll see all of the software in there for manipulating audio flows from the microphone and stuff. And maybe you can come up with your own VR engine. But for my example, I'm going to start with the Advanced FPGA app. So this app was put in here. It's a very simple app that flashes the LEDs, but it builds a framework that you can use. So one of the things I've found is that when I start off with a new system, there's usually a lot of learning and a lot of stuff that has to be set up. So it's much easier if you can start with something that's already in place and then adapt it to your needs rather than having to read all the documentation and figure it out from the beginning. So how does all of this work? So I'm going to zoom in to the RTL subdirectory. So if we look, QF Advanced FPGA has an FPGA directory, it's got other directories in it, and then it's got an RTL directory. And in that RTL directory, because you're interested in FPGA, there's several files in there, and it starts with the FPGA top. And I've got a little sort of block diagram of the top over there on the right. So there's two modules in top. There's this thing called cell macro that is kind of a bus functional model for the rest of the chip. And so it has a wishbone bus, and that's how the M4 talks to the FPGA. It's got clocks because you need clocks. It's got DMA control if you use DMA. It's got interrupts so you can interrupt the M4, and it's got a bunch of other signals for doing other things. And then there's a piece of IP, a module called the FPGA IP, which is where you're going to put your IP. And the FPGA IP can also top level can also access all of the I/O on the chip, right? So it accesses the M4 and the I/O over there on the right. So if we dive into the actual Verilog, I've cut it down. Verilog is kind of a verbose language, so I've chopped out pieces of it. But if you look here, you can see module FPGA top on the left, and you can see that the module has LEDs, the red, blue, and green LEDs, and they have 4 monitor ports that I use for debugging. You can see the module call to FPGA IP, and you can see that out of that comes the LEDs and the monitors, the signals that are going to go out of the chip. And you can also see that there's access to the wishbone bus and all the other signals. I chopped them off here because of space. And then down at the bottom, you can see that that fixed thing, the Verilog model of the rest of the chip, and you can see the wishbone bus coming out of it, and the two are connected together with signals, as you'd expect. So dive down a level deeper. Now in the FPGA IP, you don't really have to worry about the rest of the stuff except to route your signals through it to the IOs. So now down in this level, there are 3 cells. So usually with software, what we do is we want to interact with the IP, and the typical way to do that is to use a set of registers. And so the file here, the module here, is a template for registers, and you adapt it to your IP, and I'll show you that in a minute. And then the other block's your user IP. This is where your special source goes. So in my case, what did I want to do today? Well, I wanted to build something that converted letters into Morse code. I'm not very good at Morse code, so I can type in the letter A and I get a Morse code blinked out on my LED. And it connects to the real world through I/O and connects to the M4 through that register block. And then down on the bottom, there's a little piece called QL reserved. You don't need to worry about this, but this has specialized code in there to prevent the wishbone from hanging. So if you address an address that doesn't exist, that you don't recognize, it'll time out and say, tell the M4, well, that didn't work out so well. Okay, so going in a level deeper, so here's the FPGA IP. The actual module, and again, I've stripped it out, so you can see the LED signals and the monitor signals getting pushed out up to the top level. You can see my user IP, and you can see there's two sets of ports on it. There's a bunch of ports, duration, color, which come from the registers, and then there's a bunch of ports that go out to the I/O, the three LEDs and the monitors. And then if we dive down into the registers, you see the registers take the wishbone bus in and the other buses in, and they spit out the duration, color, Morse code stuff to the user IP. So wishbone in from the M4, signals out to the user IP, signals out from the user IP to the LEDs. So, so here's the register block. And of course, registers are the key to the M4 FPGA communication. So on the left is the actual Verilog IP. So you'll see at the top, it defines a bunch of parameters. So it defines a register ID address, a rev number address, scratch register address, color address, character address, duration address. And on the right, I've created a structure which goes in my house. It's a .h file, and you'll see that it's got exactly the same registers in it. It's got device ID register, rev num, scratch, color, duration, Morse code. And you'll see that they have the addresses that correspond to the addresses in the Verilog. So that's how it knows how to read, tell the Verilog what to read or write. And you'll see it also in the HAL. I've listed some subroutines I built to access those things. And then in the Verilog, you'll see that we define some routines to access, tell us when these things are being written. And down here is a piece of the code, and it says, well, look, if you're trying to write to the scratch register, then the scratch register should get the value from the wishbone data bus. And if you're trying to write to the duration register, then the duration register should get the value from the wishbone bus. And, you know, it should get byte 0 if byte 0 is enabled, and byte 1 if byte 1 is enabled, and both if both are enabled. And then down here's the code that does the read. And it says, well, look, if I'm addressing the rev number, then put the rev number on the wishbone output, the thing that's going over to the M4. So you can see it's pretty simple. You can just take this, you can change the names of the registers to your names, you can add new ones easily. You just sort of, you know, cut and paste lines and edit them a little bit. You add your registers, you add your signals, and you're ready to go. So makes it easy. Now, the other thing I usually run into when I build IP is, of course, now I got stuff in the FPGA, but I kind of need to exercise it. And I've got my M4 code, but I kind of need to exercise that too. So one of the things in the Quark SDK is a nice little package called the CLI package. And it lets you define these relatively simple things. So here I've got CLI command simple, says character, set character, and transmit character. So what that says is if I type in character, then I should call the set character function, and this is my help. If I type in code, then I should call the set code function, and here's the help for it. And so if you go down here, you can see, well, here's the set character function. It says, oh, go to the expect after the character, expect a string, which has the character string in it. And then once you get that string back, push it out to the Morse code function. Or if I want to do down here, instead of actually, if I want to get the character, then from the Morse code function, I'll read the character and I'll display it using this debug routine. So with the CLI, I can type in and send characters and get them back. And that ties over to this Morse code.c, which is part of my HAL. So if you look at the top here, I have initialized routine, which sets the various clocks. So there's two clocks going in, the wishbone clock and the main core clock. And then here's the functions. So how do these functions work? So if I want to get ID, well, I just return the registers points to device ID. Remember, we set up that register structure. So I have the base pointer, grab the value out of it. If I want to set the Morse code value, I go to the registers and I set the Morse code offset to Morse code. So again, very simple. You can just take this, you can see the structure, copy, edit, paste, and you've added in your own set of functionality. Well, that sounds pretty good. Quark SDK also has an integrated build system, which handles both the software and the FPGA. So once I've edited my RTL, which I did in this case, I just go and type make, and it trots through all of my various directories in the Quark SDK. So it goes through the startup and the HAL and the FreeRTOS directory. And in this case, I've already made them, so it doesn't have to do anything. It gets down to the FPGA directory and it says, oh, there's some work to do. So it files off QL Symbioflow, pinch out a bunch of messages. I hid them. And then when it finishes, goes through, links the whole thing and creates myself a link file. What do I do then? Well, then I go over to another open source program, which we have incorporated, called Tiny FPGA Programmer. Tell Tiny FPGA Programmer, hey, I've got a quick feather. I want to program the M4 part of it. So I'm programming my application into it. And here's my bin file that I want to program. And by the way, it's hanging on COM port 5, sorry. And when I finished, issue a reset, which will start it up. So Tiny FPGA Programmer goes through, programs my device, programs both. Actually, what it does is it programs the M4, and in this case, the M4 image then programs the FPGA, but we can also do it, just program both separately. And then you go run it. So after it resets, it comes up, it waits 5 seconds to see if you want to program it again. If you don't, it automatically starts running. And then this is the output of the Quark FPGA running. So you'll notice, Quark SDK running. So you'll notice it says Advanced FPGA Example. I should have changed the name to Morse code, but I didn't. And when it runs, the CLI pops up. So I say I want to go into the Morse directory. In the Morse directory, I want to talk to the duration register. I want to set it to 100 milliseconds. And then I want to transmit character S, and I want to transmit character O, and I want to transmit character S. So an example of actually doing that, and I'll show you on the screen in a minute, if it will let me do this. Hello. I seem to have frozen. Can you guys hear me?
Yep.
Why won't the screen advance? Because I'm typing on the wrong screen. Okay, so here's an example where you can see in the little top piece, I typed in character A, typed in character B, and I have my logic analyzer hooked up to those monitor ports. So I'm monitoring the clock I use, and when the A comes in, the start signal goes high, and then it kicks out to the LED, activates the LED with a short pulse and a long pulse. So short long is the Morse code for A. So sure enough, it flashed an A. And then it hits the stop. And then because I typed in B, it does another start and it sends out a long and 3 shorts. And that's the Morse code for B. So that's how it works. That's what I managed to run. So right now I have my trusty quick feather here. And if I go to drag up the right screen, pull this screen over here, I can say character A. And if we're really lucky, it'll actually work. So it did the short and the long. Now I'm going to say character S, which is 3 dots. Character O, not that I'm in trouble, but 3 long dashes. And then character S again. So I've just sent my SOS. And this is the end of my transmission. I guess I should have sent EOT. But at this point, that's all I wanted to show you. So I hope you see that you can now fairly easily bring up FPGA IP interact with it with the M4. We put a framework in place that makes it really easy to do that. And it's all open source.
Thanks, Tim. Hopefully everybody saw, again, how easy and straightforward that is and get the pointers. I think we will provide the slides so you can get the links as well and go experiment yourself. There are some questions popping up in the Q&A. Ruin Lind, should I answer them verbally or is there a way to type them? Verbally?
Let us present the questions and conduct the Q&A session.
Yep. Great. Thanks, Scott.
Okay. Okay, now we can see the list of questions on screen. So the first question is, given the size, what be some typical apps that each model is able to accommodate?
Tim, you want to take that?
I assume by model, well, yes. So there's two aspects to this. There's the M4 aspect that has 512 bytes of memory, so we can run fairly healthy applications on that, like Alexa kind of apps. The FPGA itself is relatively small, so it's designed basically for doing small, high speed things. So we've done apps for AI where we do very high speed, like megahertz kind of ADC sampling. We've done signal processing kind of things where we do filtering on audio signals, that kind of thing. So it's capable of doing that.
Cool. So the second question is, have you considered replacing the Cortex-M4 from ARM with an open source microcontroller?
Yeah, so in this device, the Cortex-M4 is actually ASIC gates, and the FPGA is next to it. So replacing it with an open source microcontroller would mean a whole new mask set. So we are working with the Open Hardware Group, which is a different open source foundation that's doing a 32-bit RISC-V Core 5 MCU project with FPGA next to it, and Tim is one of the vice chairs of the working group for that. So we are working on that device. The other thing I would say is we have devices with just FPGA in them, and so you could do open source microcontrollers that are just RTL soft IPs and synthesize and program them into those devices as well. So there's either one, but we're definitely working on a RISC-V based version with the Open Hardware Group.
To be honest, probably more developers are familiar with Cortex-M4s, but an open source option is always great.
It's always good.
Okay. Do you ship your FPGAs to Taiwan?
Yes, we do. We ship to Taiwan to distributors there. You can get that off our website. We also have Mauser, which ships worldwide, and then we're in the process of launching that on DigiKey as well.
Cool.
Actually, I'm having one here.
There you go.
Better.
Proof it is. Did open sourcing your toolchain bring competitive advantages for you, or did it just attract free riders?
That's a great question. It actually did bring a competitive advantage for us for a couple of reasons. One, like I said in my slides, once we put out the open source starting point for people, they ran with it and actually created new tools that it would take us a long time to do, like NMyGen, for example. So I think that actually is a competitive advantage, that by providing information, the community can actually make the product even better and more robust. So there's definitely an advantage from a user point of view. There's an advantage from a company point of view that we didn't have to, commit as much resources for as long by just enabling the community to do that. So, and we also have customers that are interested simply because they're open source and it's not proprietary bloatware like most FPGA companies do. So I think it's good for everybody in that case, not just the free riders.
Definitely cool. Okay, we only have 2 minutes left, so maybe do a short answer to this one. How to do functional verification with user IP in the software? Do you use a third-party tool? Can we monitor the value in registers for debug purposes?
Tim?
Yeah, so you can do some third-party tool stuff, but basically what we typically do is there's two ways we do the debug. You can monitor the value in the registers for debug purposes, so you can add that into your software. So you might have noticed that I have routines that let me read back all of those registers. And then the other thing that most people do is which is nice about the FPGA, is you can fish out internal points, probe points, to look at them, which is why you hook up the logic analyzer. These are small FPGAs, so it's not really practical to build in the the sort of logic analyzers into the FPGA that say a Xilinx does, but that's something that I'm sure the open source community will get around to doing, and we'll support that going forward.
Okay. I think our time is almost up, so let's do one. Okay.
Yeah, so maybe we can carry out the rest. Maybe we can carry out the rest.
Let's pass the questions to Tim and Brian so they can answer offline. And we would really thank Tim and Brian for participating in this session.
Thank you, everybody, and thank you for having us. It's been fun.
Thank you. It's great.
Thanks, guys. Bye.
Bye-bye.